Hello, welcome to our final year project presentation. And our project is about finding attractive faces around us. Basically, we have implemented a facial attractiveness predictor. And you may ask, is beauty a machine learnable concept? Well, based on recent research, experts have found that people actually share common tastes about beauty. For example, the averageness, symmetry, facial expression, and familiarity. That's why we use the machine learning to teach computers how to judge beauty. And the uniqueness of our project lies on the utilization of 360-degree camera. In our project, we use the Recon Vita 5 to capture faces around us, and then we teach our computers to judge faces captured by our 3D camera. And now I will implement in details how we did this prediction function. The first step we did is we collected our own portrait sets. We focused on 6 criteria. They are race, age, shooting angle, expression, accessory, and glasses. And based on these 6 criteria, we collected 265 portraits at first. But initially, the sizes of these portraits are different. So what we want to do is we want to keep them into the same size. And during this portrait processing, we find out that for some images, their sizes are smaller than 150 pixels, which means these faces are too small to be detected. So we decided to discard these images. And for the remaining ones, we downgrade all the larger images in proportion to 150 pixels width. Then we want to crop all the pictures into a square size. So we just keep the original bottom lines of the images and removing the top part, which is the hairstyle effect. And eventually we have 112 portraits left, and among these portraits, half of them are female faces and the remaining half are male faces. So up to here, our portrait set is ready. What we want to do next is we want to invite some students and to let them give the beauty ratings of each faces. So that's why we designed a survey. But how does our survey looks like? Well, you can see from this sample question. For each face, we asked the raters to give a score. He has 5 choices from 1 to 5. 1 indicates this face is not attractive to him at all, and 5 means this face is extremely attractive to him. And after we signed out our survey for a week, we get 36 responses, which means for each face it has 36 numbers. Then we want to take the average and use the average as the final score for these faces. But before we do this, we have to pass a Pearson correlation test to check whether we can use the average to represent the final beauty score. And the result of Pearson correlation test tells us that we have 99% confidence that our raters they share a similar preference on judging facial attractiveness. Therefore, we can use the mean as the final scores for these faces. And then we take the average and get 112 scores. So here is the distribution of the final scores. You can see that the scores range from 1 to 4.5. And next, Julia will talk about the methodology we use to predict beauty.
I will introduce our methodology in this project. Based on some previous psychological research, one dominant facial feature that determines facial attractiveness is the distance ratios between the various facial landmarks. Thus, we decided to use geometrical facial ratio to represent a face image. To extract those facial features, the first method that we use is the facial landmark detector. DLab is a cross-platform open-source library with a collection of various algorithms in machine learning, computer vision, and image processing. DLab contains a pre-trained model of facial landmass detector that is used to estimate the location of 68 XY coordinates, which can describe the shape of a facial region, such as our mouth, eyebrows, eyes, nose, and jawline. DLab is fast and accurate, It can support multiple faces detections. So in this project, we use the Python API wrapper to count the faces and detect facial landmarks. To simplify the coordinates dataset, we extract the 19 points of 68 D-Lab landmarks, which can locate the edge of a facial region. We get all possible combination of 4 sampling points in the set size of 19, which is 3,876 combinations. For each combinations, we compute 3 distance ratios, and finally we use 11,628 ratios as a facial features to represent an image. Then for the machine learning part, as mentioned by Eve, we collected 112 images. So we separated them into 100 training sets and 12 testing sets. For each image, it is represented by 11,628 floating numbers, and each one is labeled with its corresponding rating. PCA is applied to reduce the high dimension of the extracted features and remain 50 components to train our model. As both of our input and output data are numerical values, we choose to use linear regressions as our training model. To find the relationship between facial features and rating, linear regression is fast and simple, and it is good for a prediction problem. We use our testing sets to validate our trained model and achieve the correlation at 0.8191. The workflow of our attractiveness predictor is like this. With an input of a 360 image, we do image resizings, and we detect the facial landmarks with D-Lib, calculate the center point of each faces and its corresponding distance ratios. Then we apply PCA to the input data to reduce the dimension. And then we get the prediction scores from our trained linear model. The output score is marked above the face. Now let's have a look at our demo. As we can see that the facial landmarks are all detected and marked on the faces, and we count the number of faces detected and use OpenCV to draw a rectangle on the faces. The predicted score is marked above the face. For the future plan, we attempt to move our Python script to a real-time application utilizing Wikov-Vita5 API. And we would like to improve the performance of our attractiveness predictors by increasing the size of our datasets, optimizing facial feature representation, and research more on the machine learning algorithm to train a better model.